All right, welcome back. So we want to look at the first series test. This is called the test for non-convergence. And what this result says, it says that the infinite series, where the sequence is an, in other words, this is the sequence for the terms that I'm adding up, this infinite series does not converge if the limit of the terms in the sequence as n goes to infinity does not equal to 0. All right. And first of all, this kind of makes sense if we think about what's going on with the partial sums, right? In order for the partial sums to converge, the things that we're adding, if we kind of go back and think about how we get the sums in the partial, the terms in the partial sum, right? In order for this thing to converge, we have to be adding things that are getting closer and closer to 0. They have to approach 0. And so if we actually look at an example, so we were talking before about the partial sums for the infinite series from n equal to 0 to infinity of 1 over 2 to the nth. And we could see that the terms we're adding up are getting successively smaller. And in fact, they're not just getting successively smaller, they're approaching 0, right? So if we think about this, this is going to be equal to 1 plus a half plus 1 over 2 squared dot dot dot. And we can certainly see that the limit as n goes to infinity of the terms on the sequence we're adding up are going to 0. And graphically we can see this. This jump right here between successive values and the partial sum is the value of an. And we can see that that value is getting closer and closer to 0. You can't even really draw it after a certain point, right? Okay. It's also true if you have a series where the terms kind of alternate, right? It doesn't converge because the sum is alternating. So it's also true if you had the sum minus 1 to the nth. You'd see again it doesn't converge because the terms keep kind of oscillating back and forth and the sum can never converge down to a nice number. It's important to understand what this result doesn't say. So it's important to appreciate the fact that this theorem does not say that if the limit of the sequence terms is equal to 0, then the infinite series converges. It does not say that. So to give you an example of a situation where the terms in the sequence, their limit goes to 0, but the infinite series itself doesn't converge, there's a very famous example. So this is a counterexample to this statement, you might say. This counterexample is known as the harmonic series, which we're going to talk about more when we get to the integral test. And the harmonic series is the series from n equal 1 to infinity of 1 over n. So this is going to be when n is equal to 1, I get 1. When n is equal to 2, right, I get 1 over 2, and so on. And it's certainly true that the limit of the sequence terms goes to 0. So what we want to note is that goes to 0, but this infinite series does not converge. In fact, it diverges to positive infinity. does not converge. Okay, so it's important to realize that this is a test for non-convergence, not for convergence. It doesn't tell you anything about the convergence of the series if the sequence of terms that we're adding up have a limit that goes to 0 as n goes to infinity. If this is true, we can't say anything about the convergence. We can only say something about the convergence when the limit's not equal to 0. Okay, so two things to bear in mind. The first is that we want to always apply the test for non-convergence first. The test for non-convergence is one of the most overlooked tests by students. And really, it's a godsend, because if you find out that the test for non-convergence shows you this series doesn't converge, you don't have to do any work. It's like when we evaluated limits, right? What do you always try? Always try substitution. If it works, you're done. Same thing here. If we find out that the limit of the sequence terms don't converge to 0, we're done. We know the infinite series does not converge. Now, in order to apply this rule, it's kind of useful to know how various functions behave asymptotically. In other words, what they behave like in the limit as n goes to infinity. And this is a general statement about the growth of the important functions that we're going to use. So this says that the natural log grows less fast than power functions that have positive exponents, which grows less at a slower rate than exponential functions. Okay, and obviously here for the exponential functions, a has to be greater than 0. This is alpha an exponent. This is a base, and this grows less than the factorial. And so just to kind of illustrate this is a plot below. But I want to talk a little bit about the factorial function, because a number of you might not have seen this before. So n factorial is defined as 1 times 2 times 3 times ... n. Okay? So, for example, if I wanted to compute, we could just kind of start computing a few factorials, right? So 1 factorial is 1. 2 factorial is 1 times 2, which is 2. 3 factorial is 1 times 2 times 3, which is 6, and so on. And this particular function has great use whenever you're using probability theory, among other things. So it's not too, it's probably not too familiar to many of you because you haven't done a lot of probability theory yet. And if you look at a plot, this is just a little MATLAB plot I made of these 4 functions. The log function, you can't even see it relative to the factorial. Okay, so the growth of the log function is so small compared to the factorial, it basically looks like it's on the horizontal axis. Okay, the power function here I used was n squared or x squared. Depending on how you look at this, right? So this was x squared, and you can barely make it out down here. This is the exponential function, e to the x. Okay, so this is x squared. The exponential function was e to the x, and then the factorial function we've actually defined. Okay, and you can see how they grow. Now, what does this mean when you're evaluating limits? So here's the take home from all of this. When we say that one function is less than another function, so f of n is less than g of n, in this context, what this means is that g of n grows faster than f of n in such a way that when I take the limit as n goes to infinity of the ratios, g of n wins. Okay, and this limit's 0. So as an example, let me just kind of show you an example, okay? These rules claim that log of n is less than x to the alpha. I'm sorry, n to the alpha. Okay. So what this has to mean is that the limit as n goes to infinity of log n over n to the alpha is equal to 0. And we can prove this actually using L'Hopital's rule. We can prove using L'Hopital's rule that these first three statements are true. To prove the factorial function, you need to know a little more mathematics about the factorial function that we're not going to get into. But we can prove this using L'Hopital's rule. So if I go ahead and try L'Hopital's rule, notice I have an indeterminate form. I have infinity over infinity because alpha is positive. Okay, so if I use L'Hopital's rule, I'm going to get 1 over n times alpha n to the alpha minus 1. And this is going to be equal to the limit as n goes to infinity, 1 over alpha. And when I bring the n down here, I'll have n over alpha. And remember, alpha is positive. So n to the alpha as n goes to infinity. So sure enough, this goes to 0. Okay. So even though you can prove this, if you know these rules, you'll be okay. You can just use them. But it's nice to know where they come from, right? Okay. So let's just kind of look at a few quick examples, okay? So what can we say about the following infinite series? Let's see. If we apply the test for non-convergence, what do we find out? Well, we know that e to the n is greater than log n, which means that when I look at the limit as n goes to infinity of e to the n over log n, it goes to infinity. So this tells me that the limit of the terms in the sequence as n goes to infinity do not go to 0, and therefore I know that this sequence does not converge. Okay. So this is how the sort of logic works here, okay? And we're going to see this more and more as we go along, but always try this test first, okay? It really comes in handy.